design of a stealthy dynamic analysis framework for the Android systems. So generally, you may remember that because this FDP is on this malware analysis, right? So you may have think about this. The malware can to analyze malware dynamically. We have to execute those into a analysis framework, whether it is a emulated machine or the as a actual machines. So that is the main thing, but we have to be monitor its behavior during the execution actual time. Sorry, just a minute. I'm sorry for that disturbance. Okay. So because to monitor actual behavior of a malware, we have to run this malware into a analysis framework. We generally call it as a sandbox. Okay, so that sandbox can be designed using actual device or as well as on the emulated platform like this virtual machines, right? But in the virtual machines for this Android platform or this mobile device, this is a little tricky. So that will be our main agenda, that how the malware can detect whether they are running on a analysis framework, and how to design such an analysis framework so that we can fool those kind of malwares, right? So before moving, so first question is why we need mobile security. So any idea? Anybody who wants to give some or some want to highlight some point on this domain? Why somebody should worry about this mobile security? For example, your smartphone security and all those things. Anyone can just give some idea if you have. Okay, so let's
Actually,
move.
they can only put their concern in the chat box. They cannot interact directly.
Okay, so they cannot speak. That's
Yes, sir.
okay.
Yes, sir. Yes.
Oh, and it's okay then. Okay. So that for this mobile security, that there are several things that we should care about this mobile security. So the first thing is that one user activities. So if you remember that nowadays any user are more active on this mobile device compared to this desktop or laptops. Even we have observed that nowadays 90% of the time user uses this mobile phone to do daily tasks, and 10% is approximately is done by web browser or something like that. For example, you want to order some, you want to purchase something from the Amazon, or you want to order food, everything you could done through the mobile itself. And even whenever you receive some SMS or maybe the email, you can easily respond to that. So that's why the user are more active on this mobile device compared to the uh, this desktop thing. And as it is more active, so chances of infection is also more high. For example, anybody can send you a phishing email or maybe the phishing SMS. And on that SMS, you may have some link, and clicking on that link, you will actually uh, redirect to some rogue website, and then you may be infected. The other thing is that valuable data. So generally, a mobile device contains lots of valuable data. For example, your phone photos, contact details, SMSs, and sometimes we also put our bank account credentials, or our banking applications are also configured with these things. So these data may be of interest of anybody. And third thing is this always on property. So generally, we try to maximize our mobile device on time. On time is the switch on mode. So we generally try to maximize that our phone should not go out of battery. So we will just put into the charging point whenever we see that the device is out of battery or maybe going battery is going down. This property actually attracts these attackers frequently because they actually try to identify such devices which are always on, and they can infect those devices and make them as a slave. For example, if you have remembered this thing, the what is it called? Command and control servers, right? The botnet. If they will make your device as a bot for their organization, they can use this device to attack any infrastructure like DDoS attacks and all those things. And the thing is that it has multiple attack surfaces. For example, it interacts with the cell tower to facilitate incoming outgoing calls. It can connect to a corporate network if somebody is working on that, or it can communicate with the multiple websites. So any of these things can be a rogue device that can be used to infect a mobile device. For example, let's say somebody can simply put a rogue Wi-Fi network and saying that it is free, and one of us can connect to that device, and then our mobile may get infected. And sometimes we are at, let's say, some airport, and our mobile phone battery is going down, and we see some public chargers over there. And then we put our mobile phone on that public chargers, but we do not know what this public charger actually contains, whether this is a rogue public charger or a genuine public charger. If it is a rogue, you will connect to that and then your device may be infected. So this, because of that, we should more worry about this mobile security because it contains valuable data and many attack surfaces are there through which anybody can compromise our mobile devices. Second thing is that we are just talking about this Android platform. So why should somebody just look into the Android and why not other mobile platforms, right? So the first property is that it is almost completely open source. So almost means part of the things can be proprietary. For example, let's say we have several device vendors, whether it is a Samsung, Google itself, Micromax, Motorola, and any company, right? So they do lots of customization on the Android operating systems, right? So because of this customization, that customization part is proprietary, and other than this, everything is open source. And second thing is the global market share. So if you just observe the market share of this Android platform, it is approx 85%. So if attacker will see that 85% of the users are using this Android device, creating a malware for that device, they will infect this number of users. So which will give them a army of the bots, and that can be used to perform any attack on a infrastructures, right? So as a result, so malwares attackers are creating more and more malwares. So this is a statistics from A/B test, and statistics were collected from July 2025. So it contains two types of samples. One is this malware, and another is the PUAs. PUAs are not actually the malware, but a kind of malware, but not exactly malware. So the tendency is that the POM it turns into the malware in any future times. So if you remember this cam scanner app, right? So earlier this cam scanner app was benign applications, but later, after sometimes maybe 2, 3 years, the news came that it is a malware and it is exfiltrating many sensitive information from a mobile device and sending out to some other countries. So these are kind of a PUAs which may turns into the malware. So we can say that both malware and PUAs are very harmful for us. So if comparing this statistics, if we will just compare about this 2024. So in every 28 seconds, so a new malware, Android malware is born in the 2024. This is only for the malware figure. If you just account this PUAs as a malware, then the figure is 8 seconds per second. Eight every 8 seconds, one malware. That is the actual figure. So by seeing that this much of growth, we should be worry about the uh, this malware. things in the Android platform. Okay. So the next thing is this analysis technique. So you may have already studied about these analysis techniques. So generally we say that these analysis techniques classified into the three categories. One is this static analysis, where we generally just dissect a applications. We do not actually execute this. We just do a analysis on the code part, only the code. What API they are using, just inspecting the code. Then second is this dynamic analysis where we actually executes a malware into a sandbox environment. So some of the limitations are there for the static analysis, some of the limitations are the dynamic analysis. So to overcome limitation of each other, they came up with this hybrid analysis where they will utilize features or the information from both the environment to complement each other. Okay. So using these techniques, many of these malware detection work has been proposed for this Android platform, which can be deployed either on a server side, that is offline manner. For example, you are deploying this solution on a server machines, not on the actual mobile devices. Okay, and then you are doing so all the analysis offline. Or second is on a real device that we are calling this online manner. Online manner means that actual malware detection system is running on a mobile device just to detect the malware, right? So for example, these antivirus softwares are also there in the market. Those are kind of a malware detection system. Okay, so actually this server has unlimited resources. If you remember that our server are generally connected with the power sources, so we can perform both static as well as the dynamic analysis on that because we have lots of power. We can run any sample as number of time, and then we can observe the behavior of that from the dynamic analysis. And also we can use this static analysis over there. But for real devices, we generally have limited resources. So we actually stick ourselves just to use static analysis techniques. Otherwise, if we will deploy a dynamic analysis thing on these real devices, then it will slow down the smartphone speed and it will actually drain out the battery of a mobile devices. Okay. So during this offline analysis, right? So offline analysis are generally built, or you can just say offline analysis that are built around the dynamic analysis can be bypassed using these three techniques. So they can detect this emulated platform. Second is they can observe the system slow down due to the profiling overhead. For example, if you are deploying a dynamic analysis system on a mobile device, it may slow down the speed of a mobile device, right? And similarly, if we are deploying this dynamic analysis framework on a sandbox environment, so they may also observe that the number of instructions that are going to be executed per second or per minute, they may be very less compared to the original systems. So the slowdown is another thing that can be used to detect the dynamic analysis framework. Or sometimes malware uses a multiple layers to perform a malicious actions. For example, in the Android application development, we can develop application using the C++ language, even in Java, and even the combining both. We can combine both the programming language uh, uh, just to design any applications. So the same techniques malware can also use. And now just think about if we are developing a dynamic analysis system that is just observing the Java level API calls. And malware is doing some malicious tasks using this C++ native code, which is out of scope of that analysis systems. Or we are deploying this solution for C++ and the application is using only the that part. Or they are just doing multiple thing. So that based on that, we should care about design some analysis framework which can have a cross-layer profiling capability. And this is for real device. So if we will deploying any solution, the existing solution on a real device, then it will have a So for example, all these solutions that are developed for the server side using even using the static analysis, they actually uses a very heavy computation, and we can not directly introduce those application on this real device. So which because with that requires a very high resources. So based on that, we generally do not prefer on those things. And another thing is that people also give attention to this malware detection as well as this classification task. So people are not doing this thing, but these are the things that generally malware analysts are doing. But our main focus is on design this stealthy dynamic analysis framework so that malware cannot detect that they are running on a analysis platform. Okay. So let's see what we can do. So there was a framework that we have actually developed for some long back time. So that is actually designed for this stealthy, that is designed to provide a stealthy capability. So it actually contains two module. One is that std-newt. Okay, STNUT, Artmon, and Syscolmon. These are the three core components that we have developed, and we will just look how we can design such kind of analysis system so that we can bypass most of the emulation detection attacks. And then finally, we have built this NVSeal using all these three components. So if you just observe, so if you have ever developed a Android applications, right? Just to test out that it is compatible to run on different machines, or just to test our prototypes, right? So we use this Android emulators just to test whether our prototype is working or not, right? So the same Android emulators are also being utilized by this analyst to analyze a malware dynamically. So they actually run these malware on an emulator and detects the malicious behavior by actually interacting with these applications by running these things. But the problem is the same. The malware writers also inserts some code that can be used to detect emulated platform. Okay, so that to just the task is just to evade this dynamic analysis things. Not only the malware, but nowadays benign applications are also trying to detect whether they are running on a analysis framework or not. Just because they want to hide their IPs, the intellectual properties. For example, some commercial application was there. They have developed some highly sophisticated techniques just to design that application. They were also trying to hide their IP from the analyst so that the IP will not be leaked. So they will also apply these techniques just to avoid rooted devices or maybe the analysis platform. And second is that the they should provide a cross-layer profiling capabilities. Okay. So based on that, and third thing is also that the profiling capability we are uh, providing, or we are designing the profile capability, but this profiling capability should not incur lots of overhead in terms of slow down the system's runtime and all those things. So based on that, we have three objectives. So generally, whenever you do some research, you should have some uh, objective. For example, let's say why we are designing this analysis framework. So we should have something. So the one objective is just to design some emulation detection library to study that how well or how effective existing dynamic analysis frameworks are to avoid this emulation detection attacks. Okay. Second is that once you will identify that these are not capable of doing this thing, or maybe are able to do some are able to fool some attacks, but not all. Then what are those attacks? And based on that, you can design some anti-emulation detection techniques. Anti-emulation detection techniques means just to fool these uh, malware that are trying to detect emulated platforms. And then third, just to design low overhead cross profiling capabilities. And along with this, on demand services, whatever you want to provide this thing. So we should have analysis framework that can also provide you the network traces so that some analysts want to develop some malware detection system just by observing the network traffic or this memory dump thing and many other kind of these things. Okay. So if we just think about this emulsion detection, so I'm just going to discuss a little bit brief about some emulsion detection techniques and then how we will test it out the existing frameworks just to check whether they are able to provide or not. So there are five different categories. One is this unique device information. Okay. So unique device information means so our each and every device generally have some unique features. For example, IMEI values I is unique to each and every device. But in case of mobile devices or the emulated platform, it is actually fixed some 0000, which is not realistic. Okay. And sometimes to fix that thing, just not to provide a, just to provide a realistic sensor, this unique device information. And dynamic analysis framework or dynamic analysis framework designer generally fixes some IMEI values or the mobile number to a analysis platform so that whenever any malware writer try to detect that whether they have unrealistic value or null value, they will detect these things. So just to fool those things. But generally they fix this thing inside the code itself. So nobody can configure it or nobody can change this rating at the runtime. So if you are not changing this reading at the runtime, so then attacker can also identify these things and then they can release another kind of malware just to check whether they have some fixed values or not. Right. Second thing is the sensor reading. So you know that our mobile devices has lots of sensor, whether it is a light detection sensor or this gyrometer or accelerometer or GPS. There are several types of sensors. So if we are running on an emulated platform, so we do not have some sensors over there, right? Or if sensors are there, then we do not see any changes in the sensor rating. So the first defense is that if any malware or any application doesn't see any changes in the sensors data, then you can simply say that this is a emulated platform. So this kind of malware actually uh, came into the market in around 2020. So we have observed that malware samples, and then we have also came up with this design choice of emulation detection, and some of this analysis framework should also care about the census readings. Okay. So the third thing is this GPS information. So if we will just observe that GPS is also a kind of sensors, then why we should say that this should be a unique or another kind of emulation detection attacks. So this is a little bit different because this Android platform. So Android platform also provides a mock location generation API. So mock location means it actually used to generate a fake locations. So if you have remembered about this Pokemon app, right? So there was some challenges in which you have to be at certain location to enable some labels or some stages. So what people have did then, they are using this mock location API generation things and they developed a application just to fake the location inside a mobile device. They are staying at a single location, but they are saying that I am at a different location by using this mock location generation API, and they are able to unlock those stages and the challenges on this thing. So that's why this GPS information is little bit different. Then the fourth thing is that device state information. For example, our mobile is operated based on the battery power. So this battery power is actually not constant always, right? If you are running on a emulated platform, then every time they will see the same observation. The battery power is always constant. And even our this telephony signals, that is means our by mobile network, right? This signals also fluctuates a lot. So all those information if are missing in the system, then they can also detect these things. And the last is the distributed emulation detection. So in distributed is little bit tricky. So it is also based on this identical device information. That is the unique device information techniques. For example, let's say I created two instances of the same dynamic analysis framework. Okay. Now let's say we are only having a fixed value. Okay. Both the instances will also having the same unique device information. Now think about you are running two malware on it, both the instances, and both are belongs to the though both are the variant of the same malware, right? So they have the same thing, just name is different. They are connecting with the same communication server, and the server will check that I am seeing that two bots are there, but two devices are compromised, but we are seeing only the same identical device informations. If they will see this kind of information, then they can say that these two devices are emulated or possibly a analysis framework. So we should not give any command to our botnet just to do some task. Otherwise, they will be able to detect and they will also figure out other devices as well, right? So that's why they try to bypass these things. So based on that, we just selected some well-known this analysis framework. One is the Box, then Cocodroid and MobSF. These are the well-known dynamic analysis framework in this Android platform. And also we have used this vanilla Android emulator. So just Android emulator, which is come with the Android Studio. So if you just see the result, once we have evaluated against all those attacks, so you can just see if we are showing this check marks means this emulation detection library is able to detect that platform as a emulated, because vanilla Android emulator doesn't provide any defense against any of these techniques. If you just see this thing, right, they do not provide any defense against these things. So that's why it is not able to defend against anything. But Droidbox, Cocodroid, and MobSF, right? These are able to bypass only unique identity-based emulation detection attacks, where we are just employing these basic techniques. Basic techniques means we are just checking whether we have null value or unrealistic value, right? For example, IMEI or mobile number or all those things, they follow certain rules. If these rules are not followed, then we can just say that these are not a realistic values. So based on that, we are able to say that how many things can be bypassed and how what are the things that these analysis frameworks are not able to defend against these kind of emulation detection attacks, right? So if we will just see the observation is as follows. So every framework actually fails to defend these attacks. So final summary about this emulation detection is that so existing frameworks fails to provide unique identity for this telephony system. Telephony system means the IMEI value, phone number, even the mobile tower location, they can be changed frequently. All those information are not unique to a mobile devices, right? So this should be unique. Second is that they are not able to generate realistic sensors data reading. Sensor reading for the sensors as well as the GPS, and they are not able to simulate the device state change behavior. So because of that, we need some anti-emulation techniques or robust anti-emulation detection system that can hide this underlying emulated platforms and even remain undetected when we perform these attacks on through the cross layer from the any layer of the standard operating system attacks. For example, let's say you are designing some emulation detection, anti-emulation detection technique that can fool only the Java level, Java API level emulation detection attack. But people can also write code in the C++ that can be used to detect the emulation plate library, emulation environment. So it should not be like that. That it cannot be detected from any layer, right? So, but the main challenge is to generate this realistic data for the sensors. So we will just see this, what are the challenges someone should care about. We will not discuss how to generate those values. We will just discuss this challenge because of this shortage of time. So let's see what are these challenges. So first is that there are total three challenges that is to generate realistic data for sensors. So first is that every sensor's reading or every sensor's value should fluctuate with respect to time. For example, let's say you have a mobile phone in your hand and you are just playing some game or simply you are just typing. At that time also your accelerometer reading or maybe the gyroscope reading and all those things are changing frequently. Even if you are not playing anything, you are just holding your mobile phone in your hand, right? So our hands are not that much stable, right? They are little bit shaky, and little bit shaky means we have some changes in the sensor reading. So there should be changes with respect to time in each and every sensors, right? So somebody can say that, let's say simply just give random reading. We just randomly change reading to the each and every sensors. That will be sufficient for this challenge. Okay. But the second challenge is that the these sensor actually depends, sometimes these sensors depends on each other, so they have some correlation between each others, right? So for example, if GPS reading is changing, that means from location X to location Y we just moved, that means our accelerometer, gyro sensors and all those sensors reading will also be changing with respect to that thing, so that they can come collaborate these things. For example, if you just say that, let's say you have enabled a Google map just to reach some place, okay, but whenever you go into the tunnel, right, inside that GPS generally doesn't work, but still your cursor is moving. How they are generating this reading? Because of your accelerometer or gyro sensor. So they have this correlation between all those things. Okay. And the third thing is, if sometimes, let's say today we have only five sensors something. So sometimes people can introduce another sensors, right? So the capability should be there so that we can adopt any new sensors into the systems. So based on that, these are the three challenges someone should also reflect these things. So I'm not discussing how to do these things. You can always refer. There is a online video of mine based on this STD Newt. I will maybe share this link later on. You can always check in detail whatever work we are just going to discuss next. So that work is also going into the high level talk, and you can always refer in detail things on that video. Okay. So that was the challenges. So based on these sensors reading and all those this emulation detection things, so we have just developed this STD Newt. So the thing is that neutralizing the sensors, telephony system and device state information on an emulated platform. The task was this for this. So it generally contains the two component. One is this STD Newt controller, and second is which actually used to, which is responsible for launching any app inside this emulator. For example, you have an app outside the emulator, how to install it, and then how to start execution of that, and what are the other configuration that we have to put. For example, we need to fool the sensors reading, right? We have to provide the realistic sensor reading to the emulators. So this sensor reading is actually uh, feeded to this Android emulator at runtime by this STD Newt controller itself. And then second is this extended Android emulator. If you just see this emulator screen, so this is an extended emulator. So what we have did, so we have take this Android emulator code and then we have modified this code is so that we can inject any kind of information from the outside without modifying further. So we just did a customization on that, and then we have enabled the configurable environment. So this configuration environment means that you can configure this thing at runtime without changing or without knowing any information about this dynamic analysis framework. You just need to provide that. For example, I want to set IMEI value X for this emulator, IMEI value Y for another emulator. So you can just simply provide this information and then you can just fool these things. So based on that, this is the extended emulator work. Then let's dig a little bit about this STD node controller, because we have just say that STD node controller is responsible for launching an application and all those things were there, right? So how this is actually working? So this STD node controller actually has four core component. So these are the four core component: config.ini, sensor manager, GPS manager, and GPS to BTS module. So this sensor manager, actually we have developed one algorithm that you can refer in my video that I will share you the later. So we have discussed a algorithm how to generate this census data realistically, and those thing has been used as a sensor manager just to provide the realistic values for the sensors, right? Then we also have this GPS manager, right? So we are already saying that GPS is also a kind of sensors. Then why should we worried? Why should we have a separate manager for this GPS, right? The reason for this is as follows. So GPS managers is little bit different than the other sensors. So one is this correlation between this current location and the previous location, right? For example, let's say we are just simply designing this sensor manager and providing the random values. But these random values will not work for this GPS because they are actually depends on this current location, and the previous location is current location is actually depends on the previous location. For example, let's say somebody is in the Delhi and they cannot reach Ghaziabad in 5 minutes from the Delhi, right? It is not possible in anyhow because traffic is too much or all the things. Or you can just simply say they are if somebody is in Jaipur and they just reach Delhi in 5 minutes. That is not possible. So we should be much more careful about these things. So how can you do these things? So you can use a path patching algorithm. So there is a Haversine formula that you can refer to generate a path between two locations. So what you can do, let's say we can identify that, let's say from reaching from Delhi to Ghaziabad, it takes 2 hours, right? And we can divide this into the equal points, right? Then based on this equal points, we can actually generate a path for this or whole trajectory to going from this Delhi to Ghaziabad using this Haversine formula. Okay. Then the second issue is this correlation between the cell towers. Let's say you are just changing this reading, say GPS reading, but you are not changing the GPS reading from the cell tower. And cell tower is also a source of geolocation because cell tower actually is situated in some location and there are some algorithm or there are some data set that can be easily used to get the information where actually this cell tower is located, right? So the thing is that so the idea is that a cell tower and the mobile, the distance between these two things could be a, let's say, X meter. This X meter actually depends on the distance between or the area where this mobile tower is located. If it is in a, let's say, some uh, highly dense area, then the distance will be very less. And if it is a just not in dense area, let's say in the open field, then distance will be very high, maybe up to 1 kilometer, 2 kilometer, 3 kilometer, depending on the location where this cell tower is located. This range may differ. So you can just need to define some threshold. Let's say we are just talking about this 500 meter. We should not be more than this 500 meter or 600 meter that you can just define by yourself. Okay. So the thing is that how to design these things, because GPS correlation between GPS and these things we can manage based on this Haversine formula, but how to get this BTS information being changed? Okay, so for that we have this GPS to BTS module within this controller. So what is the task of this GPS to BTS controller? So it takes the current location from this GPS manager. Okay, and then they obtain the nearest cell tower ID from this open cell ID data set database. This open cell ID database is actually a database which contains the cell tower location and where it is situated. So it contains the cell ID and the location on inside the database. And also we need to utilize this SIM information. The SIM information is somehow correlated with the which cell tower we should use. So cell tower means, for example, our SIM is from this Vodafone provider or from the Airtel provider. We have some IMSI code. Based on that IMSI code, it will also divide it into the country and mobile operator and region in which it belongs to. Based on that, we can just query this open BTS location. Okay. And then we can feed this data to this extended emulator just to fool these things. Now the question is how to fool this, how to provide this data. So because the vanilla Android emulator doesn't provide any interface to just change this reading. Okay, so for this extended emulator is the workhorse. So it actually changes the Android operating system and they spoof the telephony information using this AT commands. So anybody who knows this AT command, you can also refer, let's say you want to see the IMEI value. So sometimes we also type star has 06 has, right? It will give you the IMEI value of your mobile devices. But behind the scene, they run some commands. Okay, those are called AT commands. So these AT commands can be used to get the telephony information. For example, if they are running on a emulator, the vanilla emulator, and this AT command is AT plus CGSN. Once we fire this command, it will return the IMEI value. And if it is running on a emulator, the vanilla Android emulator, it will give you the 000. But to pull these things, we actually this intercept everything inside at the CAMU layer. So CAMU layer means the Android emulator. This Android emulator is actually designed using this CAMU virtualization software. Okay, so and you can just modify this CAMU virtualization layer just to incorporate this thing and then spoof this information at the runtime. So whenever anybody is querying any of this information, you can provide them the fake information. And this information actually comes from this config.ini file. Okay. So same is with cell tower ID. So you can also provided this interface to just update this cell tower ID at runtime using this emulator console. You can use this Android emulator console. There are several commands using this Android emulator console that can be used to spoof run these things. But this interface is not there. This interface is also introduced by modifying this Android emulators itself. So that this Android emulator task was, or the STD node task was just to fake or just to hide the, or just to omit the emulation detection attacks based on these sensors, telephony services, and these things. Now the thing is that we have designed this emulation detections, anti-emulation detection system, but what about this profiling information? How to capture this, what API calls they are making, and all those things. So for that, we have used this another module that we created, which is called Artmon. So this is a framework just to monitor the API calls. The API calls at the level of Java API framework or the framework level APIs that are available in the Android operating system stack. So a student only the task of this Artmon was two. So one thing is that this STD node that we have just designed, it can provide anti-emulation detection based on the cannot provide this anti-malicious detection based on the files and properties, and also it doesn't provide the profiling capabilities. So just to propose this thing, we just build this designed Artmon. So it is a exposed framework based utility that can be used to monitor any API that you want to profile. And only you need to generate a configuration file that I want to monitor these API calls. For example, I'm just interested in the network related API calls. Just configure network related API calls. It will only monitor those things, and it will also able to pull some system properties related files and all those things. Okay, so based on that, they can modify these things. So this is the expose framework based utility. You can learn about this expose framework, and based on that, you create many utilities that you want. Okay, and it can also profile this framework level API. That is the main task for this. Now then, let's see how it is actually works. So the working is like this way. So whenever any at the runtime, let's say somebody wants to check some file information, whether this kind of file is there or not, or let's say somebody wants to check whether SU binary file is there or not. SU means the super user capabilities. For us, generally these files are available into the rooted device just to monitor each and every applications in that system. So if this kind of files are there or the Camu pipe file is there, then people can also utilize this to check whether this file is available there or not. If it is there, then they can just simply say that this is also emulated platform. Just seeing the file information, which is not the part of this disk. So for that, this Art1 generally consult this file manager, which subsequently consult with this file list. And file list has the properties. What values this file manager should return if this information is being queried. For example, if this, you will just see this thing, right? We are just using this file property and trying to open this Camu pipe file. So if this Camu5 file is there or not, so it will check whether it is exist or not. If it is exist, then what we should do? Okay. So this method, the arrows are a little bit different. So I just misplaced the direction of this. These direction are opposite side. So they will querying this thing and it will return the false value because this configuration file, the file list utility is having this information as a false. If you want to say that it is true, then you can just put this entry as a true. That depends on your configuration. You do not need to modify any other things except for this configuration file. Then you can simply say, so configuration file is already saying that it is a file is not available. So you can just simply say that it is not there and it can bypass the information. And at the same time, they will also log the information because this is also helpful for us. For example, this application are interested in checking whether our device having this kind of information or not, just to check whether they want to, uh, they are trying to bypass the emulation detection thing, or they want to bypass the sandbox analysis. So all the other managers, so if you just remember, we have different kind of manager, file manager and uh, system prop manager and all those things. So all those things actually works in the same fashion. Nothing is extraordinary to do these things. And these are very simple module, but because this expose is a very nice framework. And instead of expose, you can also utilize another framework which is also available that is called Frida. Okay, that is also very nice. That actually works on this JavaScript based thing techniques. Okay, so this was the profile monitoring. So we have just said that people or malware analyst can also write the code in C++ based thing, right? Maybe they are using this native library just to do some task. Okay. So we have just designed emulated STD node which can hide emulated platform. Then we have developed Artmon to monitor framework level API and some kind of framework level API related emulation detection attacks. What about if a malware is trying to run code through this C, which is out of scope of this framework layer API, and Artmon cannot work on there, right? So for that, we have used syscallmon. So somebody can also say that we can just create another library that can be used. For example, the native libraries are the part of the operating system. Why cannot we instrument these native libraries, right? So the native libraries also depends on the system calls information, right? So these libraries are also designed by somebody, and malware can also write their own code just using the system calls, and they are not directly using this library functions. So in that case, that will not be able to do this thing. So the best defense is you should monitor the system calls. So whenever you just monitor the system calls, then you can have more fine-grained information. And any malware analysis cannot bypass any system call related things. Okay. So the system call profiling is the next place. So if you have remember in the Linux environment, the stress is the widely used utility that can be used to check which system call has been used by this application. Okay. So in the Android, if we are running this stress on this Android machine, either we will miss some of the information if because this stress utility work on two ways. Either we will hook this stress system call on a process ID, or we will execute the application through this stress itself. But at Android platform, we do not know the actual starting or execution point. So stress cannot used directly to launch an Android application. The only possibility is that we first execute the application and then hook this system call on this application by observing the process ID of this application. But if we executed the application first and then we are applying this stress on this process ID, it may miss some of the information because for the gap between finding out this app, process ID and then applying stress is a little bit time consuming, right? You have to find the process ID and then you will apply. So at that time, they will miss some of the information. The another activity is this that each and every application is actually a fork of the zygote process. So what we can do now, let's say in forking mode, we will applying stress on the zygote process. Okay. Now, whenever we are launching any application, because this is the fork of the zygote process, so it will automatically apply to the application that we want to monitor. But in that case, what will happen? Let's say there are several other applications are also executing at the same time. So in that case, stress will also captures the system calls made by those applications, which will incur huge overhead in terms of both storage as well as the processing time. And we have already said that the profiling overhead should be very less. It should not slow down the system very heavily. So that's the main issue. So to just to observe that how much overhead it can incur when applying this stress. Okay. So we have just used one application called Caffeine Mark benchmark. So what this application generally do, they try to execute several benchmarks and then they will come up with the results that how many number of, let's say, how many instructions they have executed per second or per minute, right? Based on that, they will observe these things. And the second thing is that how much log they are generating. That is also a consideration point. So what we have did, we executed this caffeine mark benchmark, and then we have observed the some system call related things and just observe the log file size, how much log file size they are generating. So this is the statistics about this thing. So there are three configuration we have executed. One is this ideal. So this ideal means that our machine is not running any other things. Okay, except for this caffeine mark benchmark. So caffeine mark benchmark means you are just simply running this thing and no other application was running. Okay. Second was we are running caffeine mark benchmark and some background application, and then with stress, and then we are running this stress with caffeine mark benchmark and all those things. And then we are just observing the log files as whatever they are generating. Okay. So this is the overhead. If you just observe this overhead, then this is the 40x and 50x larger log file size with background processes and background processes with the browser compared to the ideal log file size, which is very much huge overhead. Apart from that, they will also slow down the system very much. That we will see later. So I think there is some question from some audience. I not seeing. What is the question?
Yes. It is the question is in IoT device malware detection can we use Android malware detection methodology?
Yeah, you need to design this kind of things. Yeah, you can design this system also. So IoT is the more this emulation detection impact is on IoT platform or as well as this mobile platform. But in case of this, let's say you want to just do dynamic analysis for this Windows-based malware or maybe the Linux platform-based malwares, right? So nowadays, most of the servers are on this virtual environment, right? So the emulation detection effect on those kind of malware is very less because every server is running on this either cloud environment, which is actually a virtualized platform, so they may not do anything. But mobile device, they should not think that mobile devices are somebody is just running, having a emulator in their pocket and they are just running Android on that. It should not be there, right? So we generally have the real device. Similarly, the IoT platform is also the same thing. You can utilize this thing because this the Android is also being used in this IoT environment. So many, for example, your wearable devices are having Android platform on that, and your smart TV also based on this Android device. All those things are there. Okay. So that's the main thing. So this is the information, and another thing is that the stress itself can be easily detectable. So how can one person detect these things? For example, let's say stress generally uses a ptrace system calls. And the ptrace system calls property is that if some application is already being monitored by some ptrace or ptrace system call is already applied on one application, right? Any other application cannot apply the ptrace on the same application. So now just think about malware can also monitor itself by using this stress system utility. And now in that case, if our analysis framework is applied on this application, this our stress will fail at that case. Or in other case, if our stress is applied first and then this application itself is launching this stress, then stress will fail from as in point of view of this malware. And when the stress will fail, then malware can also detect that this is a emulated platform. So this is not the robust thing in case of this thing. So what should do? We should have some other mechanism. So for that, we just created a system called monitor utilities, which is actually a kernel level extension, or you can simply say this kernel modules. So if you just familiar with this Linux environment, Linux is nowadays is a modular architectures where you can just create a kernel module just to enhance the functionality of a Linux kernel. So this is a kernel module. It generally has two different module. One is this kernel module itself, and this is called syscallmon, which is the name, and second is the syscallmon controller. So the task of this syscallmon controller is to just configure the syscallmon on which application we want to apply this thing. Okay, that we have to provide this information and what system calls you want to monitor. So you can configure, I am just interested in the network related system calls. It will configure for that. I'm interested in the file related system call. It will configure for that. So this information you have to provide from this syscall manager. That means the configuration files that you may have. Okay. And then after this, syscall controller takes all this list and application and then will configure this syscall monitor and then everything is being done by itself. Okay, so this is the main thing. So, but the issue is to design this syscall there is several changes. So one is this low-level kernel module support. So here we are talking about this Android emulator, right? So whatever Linux kernel comes with this Android emulators or the AOSP image, right? These doesn't have low-level kernel module support. Okay, so you cannot load any kernel module at runtime. So the simple solution is just recompile this Android kernel by enabling this low-level kernel module, and that is done. Okay, the second thing is the visibility of system call table. So system call table is a point where it maps a system call with their address. So if you will just change those address to your dummy system call location, then it is good to hook those system calls, right? But the issue is that this system call table is not visible in this Android accumulator. So what should we do? So in that case, so we are already recompiling the our Android kernel. So based on that, you can also get this system call table information because of this recompilation, which automatically solves the problem. And the third thing is the right protected system call tables. So earlier era in the very early design things. So this system call table are not in the protected modes, means that anybody can modify this system call table entries. But in this newer version of kernel, they made this as a protected. Protected means you cannot modify the entry of the system call table. So in that case, to handle this challenge, what we have did, we temporarily disabling this protection and then reinstantiating the right protection after configuring our information. So based on that, we are doing all those things. So this is nothing much uh, out of the box things. We are just doing some hooking kind of information thing. Okay. So after these three things, we just develop this InvSeal. So InvSeals, which is actually the combining all three modules, is this complete system that provides the uh, robust dynamic analysis framework, which can be not be detected by the systems. So this is just design. So one is may ask why we need this integrated solution. So the simple thing is that mostly the analysis thinks that they can perform multiple type of analysis just using a single thing. So we should have some combined system which can also provide the cross-layer profiling capability, memory forensics utility, and several things, and also hide this platform. So combining these three, we can achieve all those things. So these three systems have this STD node with NVCL extension means these things. So if you just see this graph thing, so it has Artmon, Syscallmon. Lime is a kernel module also. This we have not designed, we simply used. This is a well-known application just to dump the memory information from a Linux-based operating system. So it will actually dump the entire RAM data into the locations. And the second thing is the NVCL controller. So NVCL controller actually the combination of STD controller and the syscallmon controller just to configure all those things. And last is the NVCL scheduler. So this scheduler is just to schedule your job into the environment. So this scheduler can also be used to run multiple instances of your InvSeal in parallel, and it can configure each and every application or each and every instance properly with provided information, and they can run multiple applications simultaneously. Okay. So thus for this testing purpose, that time when we designed, we have used this ASP 7.1. So we just created some virtual environment, and then we have did these things, analysis and all those things. So that is there. So what were the first study? Yeah. So what was the next study? So overhead. So for overhead, we have studied run again this caffeine mark benchmark just to observe the overhead, and we just observe that it is not incurring much more overhead. So with Artmon and Syscalmon, system slowdown is only 1.04x. And if we will just observe this Syscalmon alone with the stress, then you can say that it is much more faster than the stress, that is 1.26x times. And then this non-detectability sensor. So we developed an application just to record the sensors reading, and we just plotted out these distributions against these things. So based on this distribution, you can simply say that detection is not possible. And when we comes with the GPS location, so we are just talking about the GPS location should also collaborate the cell tower. So we have taken two cell tower information, Vodafone and Airtel, and there to these two location, and then we have generated these things. So this is for device related. So we just created a three instance, and you can just see that each and every instance is getting the unique information. This was the things. And the last thing is the cross-layer profiling. So how can you do this? So to show these things, what we have did, we developed two applications, read dev info and set dev info. So read dev information, read the device specific information at the framework layer and write into a file using this native code. Native code means C, C++ code. And send information actually read this information from the same file in the native code and leaks this information to the server using these things. So this thing we can see through the Artmon and Syscalmon combinedly. This is the things. So this is the main takeaway of this thing. So the final takeaway is that so nowadays malware can detect this analysis platform. So we should care about this thing. So we need to design some stealthy analysis framework that can generate a realistic census data, even provide a low profiling overhead, and the have cross-layer profiling capability. If we have all these three information in a dynamic analysis framework, then your main analysis framework will be a very robust thing. And you can do, you can run any kind of analysis task on that thing. That's the main thing. And thank you. So if you have any question, you can ask, or maybe you can share me that question.
So participants, if you have any question, you may put it in the chat box. So I think the question was that you already discussed. Any other question from participants end?
No more question, then we can conclude, and I will just share you the.
Uh,
Yeah.
yes,
So
they are
if you
asking
just
for
if you
some
just
material.
yeah, if you just go in my profile, you can find out the paper as well as the study material. Everything is there, and even the whatever topic we are just talking about, that is the STD newt, that is having this sensor data generation techniques and all those things,
Okay,
right? You can also find out some videos over there.
good evening,
Yeah, if
Dr.
somebody.
Sagar.
Yeah, good evening.
It's me, Dr. Mushtaq, head
So,
of the Security Department.
Saurabh sir, or
Yeah.
let me introduce Mushtaq sir. He is currently the head of the department at MNIT Jaipur.